So I think you can all agree with me that an ML model is not, the value of an ML model is not realized until it's deployed in production. But building an ML service is more challenging than building a traditional service due to the added complexity of data and model on top of the service code. Next slide, please. So my name is Sheng. I support the engineering team at BentoML. And before joining BentoML, I was at Service Infrastructure org at LinkedIn. Over there, we built the service frameworks that power all the distributed services at LinkedIn, front-end, back-end, mid-tier. And our goal there is to develop a service framework that provides the right level of abstraction and standardization across the company so the services speak the same language, protocol. They come with observability capability support through logs, metrics, and traces. And from there I also learned the power of a good service that can bring and the value that they can offer to the engineering teams so that they can focus on what's the most important to them and not to worry about all the details of the underlying infrastructure. And this is where I see BentoML can play to the role that BentoML can play to the data science and ML engineering teams. And I discovered the project and was immediately attracted by this vision that finally an open source project can offer and empower data science teams that for the things I did at LinkedIn. So my journey joining the BentoML team was a little bit unconventional. I worked with the team on the open source side for over a year before joining full-time. Reflecting on it was a really good process. So not only that we get to learn about the project and team really thoroughly, you can do so this way a lot more better than a few conversations that you can have over the interviews. So BentoML. BentoML is an open source framework that we created for ML model serving and deployment, which has been adopted by hundreds of organizations in the world across different industries. Today, I will walk you through the considerations and learnings that went into building BentoML. Next slide, please. So if I'm a data scientist, I have a model trained. I'm pretty happy with the performance. Now I want to bring the model to online, so to realize its true business impact. The most common way to do so is to put it behind an API and serve it under an API endpoint. What are the serving solutions out there? Next slide. Next slide. So in this exercise, I will divide the solutions into two groups and evaluate them across two dimensions: the ease of use and flexibility. Ease of use is important for teams to quickly deliver value and offer good time to market for your solution. And flexibility is important to make sure that the framework that you choose can grow with the complexity of your use cases. So the first group, next slide, please. Let's call them the off-the-shelf solutions. There are many off-the-shelf solutions out there you can choose from. If you train your model in, say, TensorFlow, you can use TensorFlow Serve. If you train your model in PyTorch, you can use PyTorch Serve, TensorFlow Serving and PyTorch Serve. And you can also use something that's more generic as a Triton inference server that supports multiple different ML platforms. What they call backends like Onyx, TensorFlow, and TorchScript. To use these frameworks is relatively simple. You only need to provide the model that you want to serve, along with the configuration files, usually in the form of YAML. And these frameworks usually come with pre-built server binaries or Docker container images. And you can just provide the three to form your model server. And these frameworks are great for low latency serving because the model runtimes are specialized and they're highly optimized for performance. Because these runtimes are optimized, they can usually saturate and utilize underlying hardware really well. Next slide, please. However, these frameworks are not very generic and to customize. First, they are written in different languages and frameworks. If you develop models using multiple ML frameworks, you'll end up having to use different solutions. And to coordinate the communication across them, you usually have to write another service just to orchestrate the communication and with the different ML services. On top of that, the inference rule is defined by declaratively through YAML files. YAMLs are simple, but YAML complicates development. Not only do users still have to learn all the fields, the semantics behind the configurations available to a YAML, they cannot really iterate and test it easily with YAMLs and images, because you have to, every time you change something, you have to restart a server, restart the image. The image is pretty heavy to restart, and you don't have good visibility into what the image is actually doing. Next, please. Second, the model inference is really just a small portion of what ML service does. These solutions do not really offer a good way for defining your custom business logic. Data validation, feature transformation, input and output types are usually limited to just tensors. But in the real world ML service use cases, you also have things like JSON, tabular files in the forms of audio, video, and images. Next. And lastly, these use cases, many use cases require things like model ensemble type of inference to serve the actual use cases. Multi-model inference means that you put multiple models together, either put them in sequence or in parallel, and together they form an output prediction for the use case. And most of the out-of-the-shelf frameworks do not support this use case very well. They support single model, but some do. Like Triton Inference Server has an ensemble support, but that introduced another limit, is that now you're putting all the models in the same image or in the same server. They're forced to run in the same runtime on the hardware to deploy the server on. And those runtime or hardware may not be the most optimal for running these models. At the same time, the models cannot scale independently because they now have to scale with the server. Next, please. So off-the-shelf solutions are pretty easy to use for simple use cases. They're great for loading, staging, serving, but they're not that flexible because the frameworks are very language framework specific, and they're configuration driven. They're inflexible for defining custom use cases logics that have very limited multi-model support. Next. So that brings us to the second group of, next please. That brings us to the second group of solutions, what I call the in-house DIYs. And this group of consists of like frameworks using Fast API, gRPC, and Golang that help you build your ML service from scratch. Because these frameworks are so generic, you can practically do anything with them. And one solution is to package your models and custom logic in the same server. And you can inherently define any model inference logic, different control flows, different conditionals, and any logic that stitches the model together. The problem with this approach is that, again, you're putting multiple models in the same runtime. They may not be most optimal to run on the hardware that's optimal for both models. And second, the models, again, similar to the Triton Inference Server case, you cannot scale the model themselves freely, independently as a server. Next slide, please. And alternatively, you can introduce microservices architecture into your solution. Now that you can deploy models and your custom logic independently, they can scale independently, run on the hardware runtime that is most optimal to them. And you can define the service logic such that the multi-model inference is in the graph that you like. However, using this solution, you're also bringing in the complexity of distributed services. So now all the problems that distributed services face, you now have to solve. Things like service mesh, service discovery, load balancing, RPC, backward compatibility, all that, you name it. And regardless of which architecture that you choose here, you still have to work with Docker for containerization and Kubernetes for deployment. So the bottom line is that building ML services from scratch is very hard, and the skill set is not aligned with most data science teams, whose primary focus to deliver value is data, but not building complex distributed systems like this. While flexible, this group of solution comes with very high engineering cost and time to market, which makes them practically unaffordable to most teams. So next slide, please. So having learned the two, so the in-house solutions is flexible, but not easy to use for the reasons I just described. So they belong to the bottom right corner of this quadrant. Next slide, please. So before we talk about what solutions are in the most optimal, the dream quadrant, let's first explore what an ideal solution in this quadrant should look like. First, the solution should be flexible for defining custom business logic and for multi-model inference graphs. Instead of using YAMLs, maybe we want to do so imperatively with Python. So if you're not familiar, declarative programming is a paradigm that you define what the program does, where the imperative programming paradigm is describing how the program should do it by giving a step-by-step instruction. We think that imperative programming is more natural when it comes to defining custom business logics. On top of that, the intention of YAML is to simplify business logic for users without having to learn a new language. But YAML often fails to do that. On the other hand, we already have Python, which is already very common programming language skills that's known to this data scientist user group and has great community support for ML libraries and data science libraries. So instead of defining the inference logic declaratively through YAML, we think it's more advantageous to do so with Python. Second, we want the different workloads to run on the most optimal runtimes and hardware profiles. This time, not that we only have the compute-intensive models that run on GPU or multi-core CPUs, we also have the potential IO-intensive logic, such as pre-processing, feature transformation, accessing an API or database for data. On top of that, these workloads should be able to scale independently instead of having the replicas statically defined in a container. More so, the workload should be automatic scaled based on the hardware utilization. Third, we want the deployment to be in the most optimal format for the target environment. For example, if I'm just developing a very simple proof of concept, I should be able to just containerize it and deploy it to a serverless environment like Lambda. But if my team operates our own clusters, the same service should be able to be deployed to Kubernetes without changing a line of code. So other deployment targets include batch inferences on Spark, streaming inferences on Kafka and Flink. The bottom line is, again, the user should not have to rewrite their service just to deploy it to a different environment. Last but not least, we should keep the cost of development low and by abstracting the details of the complex distributed systems and networking. Next, please. Next, please. So all of these requirements, oh, sorry, one before. So all of these requirements we see here are considerations and motivations that led us to building Bento ML. Sorry, next now. So Bento ML is an open source framework for ML model serving and deployment. It offers a unified model serving API that supports the most popular framework out of the box, TensorFlow, PyTorch, Onyx, and this list is growing. It offers a SDK in Python natively for defining custom logic and multi-model inference. Bento ML also standardizes the deployment process through the Bento artifact to allow you to build once and deploy everywhere in the most suitable environment for the workloads itself. And last but not least, the Bento ML is Python first, so it natively integrates with other ecosystem toolings like Kubeflow for continuous retraining and deployment. Next, please. So next, we'll look at an example of, sorry, the code may be a little bit small. I'll talk about what each part is doing. So this is a example of a Bento ML application that does a credit application. So next, please. what we do here is we have an application coming in. We first run it through a fraud detection model to determine whether the application is genuine. And only if it is deemed genuine application do we fan it out to 3 different risk assessment models. And at the end, we combine the results of the 3 risk assessment models into a well-informed decision. Next, please. So first, we define the models and the runners. With BentoML API, so with these models are, the fraud detection model is written in PyTorch, and the risk assessment model is written in scikit-learn. So with the BentoML PyTorch and BentoML scikit-learn, we can load the models that we previously saved and convert them to runners. Runners is a concept in BentoML that represents a unit of logic that can be scaled independently. And also, next please. Runner also supports adaptive batching. Adaptive batching is when you want to group multiple requests and do inference at the same time. What the runner does here is that it waits for a configurable amount of time for the request to arrive. And without waiting for too long, this is also configurable. If it feeds the request to the model and returns the inferences back. Doing adaptive batching, allow us to leverage the vectorized and parallelism supported by the underlying hardware. And doing batched inference is a lot more optimal than running the individual requests iteratively. Next, please. You all should know this. Next, we create a service. We call it credit application, and provide them the runners that we created, the fraud detection and risk assessments. This will tell the service the structure that is required, a list of runners that went into the service, and also the models needed by these runners. So later we can package them together in the same bento. Next, please. The more interesting part is the API definition. First, we look at it defines the input and output as JSON. But besides JSON, there are other inputs you can support it natively in BentoML. You can have tensor, tabular, or files of any form, images, audio, video files. And in the application, it first fetches the features asynchronously by calling a feature store providing the input data user ID. With the features together with the input data, it'll be fed to the fraud detection model. And we have a conditional here. If it's deemed fraud, it will not continue the application, it will just reject. And only if it's genuine do we feed it to the 3 risk assessment models simultaneously. So these inferences will happen together, and we'll group the response together, post-process the response, post-process the results of the 3 risk assessment models, and return the response. You can see this definition looks and feel like a single node, single module Python application, but when it's deployed, it's actually capable of deploying it distributedly, allowing it to run in parallel and maximize the hardware utilization. Next, please. So when we look at the waterfall graph of the actions here, we first do pre-processing, and then we wait for the fraud typo here, fraud detection results to return. But we're able to run the risk assessment model simultaneously on 3 different processes or 3 different independent workers and group the response together. And we're able to do this because of the different deployment modes that natively support in BentoML. First, next please. First, we have container-based deployment. So the business logic defined in API runs in the API server. We can have multiple instances of it to work around because it's written in Python, so we can have multiple instances of it to work around the Python GIL limitation that introduced the limitation on parallelism. And we also have the runners. Runners can either deploy as a singleton if it's capable of utilizing the underlying hardware, a multi-core CPU or the GPU, or deploy as multiple instances in the container if it's not able to utilize the multi-threading capability. Next, please. We also have Kubernetes deployment. BentoML provides the Bento deployment custom resource definition, the CRD. allowing API servers and render to be deployed as pods that can be scaled separately. So you can scale the API servers because they're written in Python on the single core CPU nodes, at the same time allocates GPU pods or multi-core CPU pods for the models you run, and they can scale independently from each other and auto-scaled as well based on utilization. Right, next. So put it together, we discussed the two groups of model serving solutions, the off-the-shelf solutions that are optimal for serving single model, but becomes inflexible as the use case becomes more complex. And we have the in-house solution. They're very flexible to build custom business logic and inference graphs, but they have very high engineering cost and the time to market. And lastly, we also described what an ideal solution looks like for production scale model serving. It should have three aspects, right? First is it's capable of customized business logic definition and inference graphs. Second, it should provide optimized runtimes and hardware scheduling that allows independent and automatic scaling. Third, it should support multiple deployment environments without having users to rewrite their service. Okay, next. So thank you. That's all the talk we have today. So please check out our Slack community for model serving. And if you find this talk useful, please show your support by starting our project. And next. Yeah, and also thank you to the sponsors. Thank you to all the speakers and the work released for putting this together. Most important, thank you to the community. Questions?
We do have a few online. So the first one is, how do you batch prediction with multiple models in the same predictor? In case of batch, where do you store the results? Do you start all the models per batch request?
We need multi-parts to this question. What's the first part?
How do you batch prediction with multiple models in the same predictor?
Each model is put inside is represented by a runner. So the runner is the unit of execution that can be scaled. And the batch happens at the runner level. So we have, for each model, we batch it together, but we don't batch across multiple different models, if I understand the question correctly.
And the second part was, in case of batch, where do you store the results? And do you start all models per batch request?
The batch is returned to the caller immediately. It's not that where we store the model. So I think the misconception here is these are online services. So a response needs to be returned in a more real-time manner. So it's not stored in a temporary storage database or in memory or anything. It just returned back to the caller.
And next question was, do you have support for feature stores?
BintelML does not natively offer the feature store support, but you can freely integrate with all your favorite feature stores out there.
Do you have support for fractional GPU requests?
Very good question. Fractional GPU support, we have support that you can schedule an arbitrary number of runners on a GPU so that they combine take a single GPU unit. And in our Yatai, which is our deployment platform that I mentioned here, we're looking to introduce support for advanced GPU-based scheduler so that you can schedule your deployment based on GPU fragmentation.
Is there any plans for providing auth2 feature? I can't see. Hold on one second. I can put my glasses on now. Is there any plans for providing auth2 feature to BintelML's Yatai for user identity and access management?
If I understand the question correctly, is asking if Yatai's identity and user management can be expanded. It's in our roadmap. We don't have a concrete timeline yet, but do talk to us in the community. We can discuss prioritizing this.
And the last question we have for you is, what is the benefit for deployment working with Kserve together with Bento ML compared to using Bento ML only?
Kserve, I think, offers scale to 0 today, which Bento ML does not currently have. But Kserve and Bento ML can both fulfill the remaining of the use case quite well.
Okay. And then we will have one more. What about metrics from inference graphs? Does it emit Prometheus metrics?
Yes. So the observability capabilities come out of the box. So you have the logs, metrics, and traces integrated with Prometheus, open telemetry. You just have to plug it in.
Okay. And I think that's the last question. So. Oh, got one in the room while I'm setting up the next speaker.
I saw online that you guys offer some coverage for H2O runners. Can you talk a little bit about like the scope of coverage for H2O?
So H2O was a framework that we supported back before 1.0, was in 0.13 versions. And from 1.0, we focus more on delivering the product more. So some of the frameworks that we used to support are not yet in 1.0, but we are actively working on bringing the framework parity to all the different ML frameworks that we used to support in 0.13 to 1.0. So H2O is not currently one of those frameworks, but it's in the work.